Hello, everyone. Thank you all for coming to the PIBBSS Speaker Series 2024, PIBBSS Symposium, Fellow Symposium 2024. The next speaker is Wes Erickson. Thank you for coming to talk with us, Wes, after the 3-month fellowship. For the audience, if you have any questions, please use the Q&A function. There'll be a 15-minute Q&A at the end of the 45-ish minute talk. And if you'd like to chat with the panelists outside of the recording, please stick around after Wes's talk. We will open breakout rooms where you can talk to all 4 of the speakers from today. Take it away, Wes.
Great. Thank you, Deshaun. Can everyone see this okay?
Oh, yeah.
Great. So, hello, everyone. Thank you for coming today. Today, I'm going to talk about heavy-tailed noise and stochastic gradient descent, and where the heavy tails arise within stochastic gradient descent. And I'm going to start with, here's a brief outline of my talk. But I'm going to start with some motivations as well as some perspectives on AI safety before I get to some general background of heavy-tailed noise and specifically heavy-tailed noise within stochastic gradient descent. And then I'll discuss some of my preliminary results and some outlook for future directions. So to start, motivations. So my view of the current state of machine learning is that we as humanity are scaling up machine learning systems on top of a foundation that we don't necessarily understand at a deep level. However, even though we don't understand that, I expect that our capabilities will continue to improve even if our understanding doesn't improve. And that's, historically, we've seen that with more data and more compute, our machine learning systems have become more capable. And that doesn't necessarily require great improvements in our understanding of the fundamental aspects of it. And, forgive my cartoon, but, this is a schematic of, we have, stochastic gradient descent, linear algebra, and, heavy-tailed noise as, these are things that are kind of buried in the foundations of these machine learning systems. And whether or not these, assumptions that we make about these systems are good will potentially have an effect on what sort of advanced systems that we end up developing. And when I've been learning about, machine learning over the past couple of months, I've found there's several questionable assumptions that are commonly made about noise distributions, as well as maybe I shouldn't say ignorance, but unknowns about basic machine learning tools. And kind of to expand on that, so it is very common to assume that non-Gaussian noise doesn't either exist or it doesn't persist in machine learning systems. And that's for, an aspect of convenience, as well as there's been some arguments that this has been attempted to be measured and that it doesn't exist. And then there's also these areas where we, don't necessarily have as deep an understanding about something that's so fundamental. So stochastic gradient descent is a an optimizing algorithm that's underpinning a lot of what we see in machine learning, or similar optimizing algorithms. But there's so many aspects of it that aren't fully understood. Some examples I've listed here, but kind of important ones include why stochastic gradient descent seems to generalize so well compared to algorithms like AtomW or even full batch gradient descent. And there's other phenomena like grokking, where you'll see that training will when you're training a machine learning system, you'll end up getting phenomena where the training loss will hit some sort of plateau, and you'll see no changes in the training loss. But despite that, after training, on the same data, you'll get sudden rapid decreases in test accuracy, or rapid increases in test accuracy. And that's a phenomenon that has many explanations for it, but I would say that it's not certain as to which one of these ones is most accurate. And I won't talk about all of these, I think, but one particularly interesting one that's relevant for heavy-tailed noise is that it's been found that the Hessian of the loss function, the eigenvalues of that ends up following a power law, and having that like be an empirical result, and having those possible connections to other power laws that end up arising within within these stochastic gradient descent systems, like it seems like something that's like very very interesting, but it's also like something that's not yet fully understood. Now, I would just like to say that all of these areas that I'm talking about, I think that I have some reasons to think that they have some connections to heavy tails and to heavy-tailed noise, but I won't be like discussing all of those today. But if you're interested, feel free to ask about this in the breakout rooms, or get in contact with me afterwards, and I can share kind of my speculative ideas about some of these relations. But moving on, though, one of the kind of areas that I feel that we don't understand as well is actually even the whether or not stochastic gradient noise is heavy-tailed or not, and that's actually one of the main questions that I'm somewhat curious about, even though that this seems like it should be a relatively simple question to answer. So I'm now going to talk a little bit about heavy-tailed noise in general, in case this isn't something that you're very familiar with. And to start off, I'm going to give a little cartoonish cautionary example. So imagine that you're a data scientist, and your customer gives you a list of numbers, and they want you to kind of model it for you. And you do what any data scientist might do, is you take a look, you find that, oh, it seems like it's got a mean centered at 0, and so you plot it on a histogram. And if you get something like this, you might think, oh, I might as well fit this with a Gaussian. It looks pretty round, pretty bell-shaped. And you send this model back to your customer, and your customer goes and implements this model in whatever systems they're using. And some time goes by, and they come back to you, and they say something is going wrong. And they show that most of the time your model seems to be working pretty well. Like, in fact, 99% of the time, this model is a good model. But that 1% of the time, you actually have these big jumps. And you'll notice that this largest jump here actually is larger than the sum of every single other change, every single other step in this whole process. And that's because this was not actually a Gaussian distribution. This was a heavy-tailed distribution. So even though it looks very bell-shaped, if you use things like, basically, if you ignore outliers, you might get behavior like this. And this is something that, in principle, could happen within a machine learning system rather than, you and your customer. It's actually something that could happen on an internal level somewhere if heavy-tailed noise is present. Now, so frequently, in all sorts of different mathematical models, people will make Gaussian assumptions. And they might not even do it explicitly. They do it implicitly by using some other model. And that includes, using p-values, using standard deviations or variance as meaningful measures. If you use Langevin equations or Wiener processes, and diffusion equations or Fokker-Planck equations. And of course, if you ever do any sort of outlier removal or clustering algorithms, these can implicitly assume normal distributions for your data. And the reason that's like fine most of the time is because most of the time it works. And the reason it works most of the time is because of the central limit theorem. And if you're not familiar with this, I think most of you should be familiar with this. But basically, if you have a sum of a bunch of random variables, the distribution of that sum will end up converging to a Gaussian distribution for large n, as long as your random variables are independent and they have a finite variance. And so this is like a pretty robust theorem. And even if you relax some of these assumptions mildly, you'll actually still get the same result. But if you actually have infinite variance for your distributions, this does break down. And if you assume a Gaussian when you actually have these infinite variant distributions, then you end up not having this sort of convergence. What actually happens is there's an alternative convergence algorithm, the generalized central limit theorem. And essentially, you take a sum of these random variables that come from a heavy-tailed distribution, you'll get an alpha stable distribution. And the functional form of that is not something that you can write down. But in this case, it doesn't really matter. Most importantly, what we're going to focus on is just that it has power law tails. And if you take a sum of variables drawn from power law distributions, they will remain power laws. So these power laws end up being persistent if you're doing some sort of additive system. Now, so for similar reasons that the Gaussian distribution is important, these heavy-tailed distributions, these alpha-stable distributions are kind of a prototypical heavy-tailed distribution. So that's why we are often going to be talking about these alpha-stable Levy distributions. And so they are kind of our prototypical heavy-tailed distribution, and they're characterized primarily by their power law index, this alpha. Now, just to give you some taste for what these distributions look like, here's a distribution of a Gaussian distribution compared to a Cauchy distribution, which is alpha equals 1. Oh, sorry, 2. Alpha equals 2. And in contrast, here's what a Gaussian random walk looks like. So each of these individual steps is drawn from if you look at this process, you're adding a Gaussian random step at each time step, you'll end up getting Brownian motion, basically. Versus if you take random steps drawn from a Cauchy distribution, you'll end up getting something that looks more like this, where you have these large jumps. And it's interesting to note that while these visually we can see much more dissimilar behavior between these random walks compared to these trajectories, or sorry, these distributions. And that's just, humans are not like paying attention to these tails as much as they probably should be. Now, so there's some broad motivations for why we should care about these heavy tails. And basically it's because if you assume a Gaussian distribution when it's not, you will end up underrepresenting these large rare events. And these large rare events will be more important than all of the small events. And similarly, if you truncate distributions, you're kind of going to lead to the exact same issue. And in terms of like moving to machine learning, I think there's like kind of two additional questions that are useful. So basically, will machine learning systems like implicitly learn to ignore high damage outcomes? And that would be kind of a cause for a cause of catastrophic losses. And alternatively, on a positive note, are there any like mechanisms and processes that actually generate heavy-tailed noise that are actually signatures of something that we can use it as to give us useful insights about what sort of behavior is happening, for example, during the training process? Now, moving on to heavy-tailed noise in stochastic gradient descent. So the first paper that studied this, I think this is Simsekli in 2018. And they did a really interesting thing where they're looking at training over time with MNIST on MNIST data. And what they do is they're taking all of the gradient weights. So the gradient of the loss function, if you take all of the components of that gradient and treat them as independent variables, and then look at the distribution of those variables. And they find that it ends up looking like one of these alpha stable distributions as opposed to being a Gaussian distribution. And the reason that's sort of an interesting approach is because it's not clear that, well, in fact, it's suspect that you would take all of the weights and say that they're independent, even though weights of different layers are going to be biased and trained in different ways. But nevertheless, they did do this, and they found that it apparently has these very heavy-tailed looking distributions. Now, another thing they did was they decided to automatically characterize these gradient noises over time as using a estimator for this tail index parameter. So I guess these aren't over time. These are as a function of width and depth. But essentially, you'll notice that all of these are between are less than 2, for instance. And so these are all clearly, their estimator function is clearly saying that these are heavy-tailed distributions. Now, there are some issues with this approach, and this is the first paper that I read on this. And I thought of some, clear ideas on how to be more robust as to demonstrating that you actually have these alpha stable distributions. For instance, actually looking at the distributions of these weights directly would be, a good indicator. Now, another paper that I actually read at the same time, which I thought was kind of a serendipitous, was apparently in biological systems in brains, you actually see heavy tails in the distributions of the number of synapses for each neuron. And the fact that these are something that are arising in biological systems, as well as having them arise in these stochastic gradient descent systems, is like, that seemed like there has to be some direct connections to learning. And that was kind of like part of the impetus that made me decide to go down this track. Now, it turns out that this this analysis of tail indices was not completely clear. And this paper actually got a lot of criticism. And there's multiple papers that actually question the validity of these results. So, for example, we observed that for batch sizes 256 and above, the distribution is best described as Gaussian. We conclude that stochastic gradient descent noise belongs to a particular distribution class that is neither Levy nor Gaussian. We empirically verify that stochastic gradient noise is highly similar to Gaussian noise instead of heavy-tailed Levy noise. So it's and these were published shortly after this initial paper, these were actually when I started this fellowship. 2, 3, and 4 were the papers that I actually noticed right away, and so I thought that this was sort of a contentious issue, and I wanted to kind of look deeper because it seemed like the evidence that I saw in this Seckley paper was actually, stronger than it would be surprising if there was no heavy-tailed distribution present there. And you'll notice that this last paper is published in 2024, and I actually only noticed it about a week ago, but it solidly shows, you can see that this assertion, Levy distributions provide a better fit for stochastic gradient noise. This assertion was purportedly debunked and rebounded to the Gaussian noise model that had been previously proposed. This study provides robust, comprehensive empirical evidence that SGN is heavy-tailed. Unfortunately, since I only saw this paper recently, a lot of my initial preliminary work was basically trying to demonstrate that we do have these heavy-tailed distributions. And so I ended up replicating some of the ideas from this paper. However, it does show that this research track is at least well motivated. So I'm now going to show a few of these preliminary results. These are in a fully connected network with ReLU activations that are 9 layers deep with a width of 50. And I just have a little schematic here to show what area of the network that I'm looking at the distributions of the weights or the noises, depending on which one I'm looking at the time. So in this first plot, I'm showing the distributions of gradient noises by layer. The layers are not labeled here, but we can see that these gradient noises are very heavy-tailed. They span 5 orders of magnitude, but these aren't, if you look at them, they're lumpy. These are not distributions that you would expect if the generalized central limit theorem had been robustly active. It's essentially showing that these are not, while they are heavy-tailed, they're not, the mechanism behind that is different, and something kind of curious is going on here. Using a estimator like the Seckley group was doing on a distribution that looks like this is not a good, robust way of demonstrating that you have a alpha stable Levy distribution. So instead, it seemed like a good idea to look a little bit more fine-tuned. Sorry, that's a loaded word, but looking at just a portion of the weights. So here I'm looking at evolution of the weights over time. So these are just essentially the sums of the gradient noises over time. And you can look, if you look at them, you see that they have different characters. So like some of these are more Brownian-like, whereas other ones have these large jumps going on. And these look very much like that Cauchy random walk that we saw earlier. And to me, this is like a very strong signature that you have these heavy-tailed noise present, but they're not present universally among all weights. Some weights seem to have these present and other weights do not. If we look a little bit more closely, we can see that these are very notable jumps. And when a singular jump, has more weight than 10,000 other steps summed together, that's very indicative of having a heavy tail distribution. There is something to mention, though, is that what we're doing here is a little bit different than what the Simslecki paper was doing. We're looking at the weight over as it evolves over time, whereas what they were doing is freezing the parameters at a particular optimization step and then repeated sampling. So what we're looking at right here is more of a dynamic process where you're taking a step in the optimization algorithm, sampling the gradient, and then taking another step in the optimization algorithm. So it's definitely sampling a different distribution. But it is interesting to note that that distribution, definitely appears heavy-tailed. In contrast, if you actually if you fix the optimization step and look at individual gradients, so these are actually individual weights, distributions of individual weights that we have repeatedly sampled at a fixed optimization step. You'll notice that this orange one here is basically looks Gaussian, and it cuts off very, very fast, whereas some other ones seem to have heavier tails that span 3 or 4 orders of magnitude. However, what's very interesting about this is that the tail index is actually extremely heavy. This tail index that we see here, minus 0.8, that's something that you wouldn't it wouldn't be normalizable if you actually extended it. So it is guaranteed to be a finite distribution, a finite extent it has to have a cutoff at some delta W. Now, that is kind of unexpected because this is it's still extremely heavy-tailed, and to me it seems like it would be a very pathological distribution, and I haven't really seen this pop up in very many cases. So another interesting thing is that as you change what layers you're looking at, you do see some different changes in character. So towards the center, you see more Gaussian-like motion and less of these heavy-tailed jumps. And as you move towards deeper layers, you find that these layers are almost fixed. They basically settle down to some sort of constant and have maybe some very small amount of motion. So the heavy tails seem to be most strong in these shallow layers and not so much in the deeper layers. So another interesting thing is if we look at changing the learning rate. So before we were looking at a somewhat large learning rate, but if you look at a smaller learning rate, you get much more Gaussian behavior, and this is somewhat expected. But you'll notice if you actually look closely, it's not completely Gaussian. We actually have some what looks like levy motion. It's just sort of stuck in a well, and that's actually a really cool observation that we are, while we still have this heavy-tailed motion, it's not actually affecting the dynamics. And effectively, this sort of heavy-tailed motion is basically indistinguishable from a Gaussian distribution because the tails are clearly cut off at some point. It's not able to exit this well, and so the effective tails are truncated. And so sort of the conclusion here is that these lower learning rates hampers jumps. And that's actually something that you do see if you turn down the learning rate of stochastic gradient descent models. You get less of the generalization advantages that you see with stochastic gradient descent with larger learning rate. There's some other parameters that can be changed, such as if we change the width of our network, we actually see that the power laws that we see change in their exponent. And to me, this is actually interesting because it suggests that that these power laws may be directly related to the architecture of the system. And that's actually not completely unsurprising, but it seems like there should be some sort of way to, analytically derive what these power laws should be from some sort of character of whatever this architecture is. And let's see. Okay, but collecting all of that, we had that controversy where different papers seem to be saying different things about whether or not the stochastic gradient noise is actually heavy-tailed. And kind of the main solutions to this controversy is that the weights need to be looked at individually. You don't treat them as independently indistinguishable variables. They are a weight in layer 1 is different than another weight in layer 1. Much less, looking at a weight in layer 1 and comparing it to weight in layer 2. It's like you have to look at these weights individually and their evolution individually if you're looking for these, if you're trying to characterize the distribution of the gradient noises for that weight. Kind of a second conclusion is that estimators are not a great tool in isolation for verifying heaviness. And so they just need to be cautious in using them. And this third one I think is actually very interesting, is notable differences between the stationary step distribution and this dynamic iterative step distribution. And basically, if you're looking at these individual steps, we see this extremely heavy-tailed distribution. Whereas if you look at the sort of dynamic steps, you actually get a more expected normalizable distribution. And finally, we see that various parameters and architectures will have large effects on these noise characteristics. And so these different papers that were, some finding heavy-tailed noise and some not finding heavy-tailed noises, they were not necessarily always comparing the exact same statistics. And because of that, unclear statistics that they were sampling, they were saying that they were sampling one thing and that the other person was not sampling this. Basically, in order to compare your results, you need to be sampling the same thing. And kind of what this most recent paper has shown is that looking at the weights individually is a robust way of looking at this data, and it shows that there's heavy-tailed noise. So in terms of some future work, one of the things that hasn't really been determined robustly is the origin of these heavy tails. There are some hypotheses, but those have not been confirmed. One idea that I was curious about is whether or not these whether or not individual samples basically would be pushed into the tails versus other samples, and if there's some sort of characteristic about those samples. Another aspect that I think is really interesting is using these heavy-tailed noise measurements as a signal, and it's possible to look at some systems that show, say, implicit meta-learning, and basically see if this heavy-tailed noise arises during that learning process in certain situations. Now, I've also done some preliminary work looking at these noise distributions and transformers, but the transformer architecture seems to have not as prominent heavy tails, and I'm not sure if that's something that's if it's completely gone or if it just has if it depends on what sort of system you're training it on. Now, I've also seen some papers that talk about the using various statistics to detect the onset of a phenomenon like rocking before that process actually occurs. And I think that looking at these sorts of noise distributions could also be a good signal as to what's happening in one of these processes. And yeah, I think that about covers everything I'd like to share today. I'd like to thank my mentor Clem, as well as the PIBBSS organizers and the other fellows, and all the LISA members that I chatted with over the last couple months. Thanks for listening.
Thank you very much, Wes. All right, we don't have any questions in the Q&A. Attendees, you can raise your hand if you have a question. I also invite past panelists who are listening to also ask questions if they have any.
Okay.
A question in the meantime: is there a promising path of research that you are not planning to take, but that maybe you would like to invite other people to do?
That's a good question.
Thanks.
So one aspect that I think is pretty interesting is there's been some well, it's hard to say exactly what I'm planning on taking further work on, but
Right.
There's been some interesting work that looks at fractal structure of these stochastic gradient descent models, and instead of analyzing these as a heavy-tailed diffusive system, they analyze it as a sort of a fractal-like structure. And there's some deep connections between these noise distributions and fractals, but they are statistically often very different. And I think that would be kind of a interesting competitor in a sense to the framework of using heavy-tailed noise.
With the other work on fractal structures, you mean stuff like Simplex, Adam Shai, and Paul, or
I think
something else?
like fractional Brownian motion and as well as like I mean, I'm actually a little less familiar with this, so I probably am speculating beyond what I can
That's
share.
fine. We're here for the speculation. Yeah, but yeah, that's interesting. Like, if there's threads that you don't want to pick up but could be interesting, one thing that people don't usually do is communicate them so that others can pick them up. But yeah, we've had recently the hackathon, and that was pretty great for doing that kind of things. Just like letting other people run with your idea in directions you haven't thought of. Cool. Awesome. Yeah, any more questions? Give a couple more seconds for the audience. none so far. All right, let's take a. Actually, let me stop recording now.